So homework 1 is released. I just at this moment realized I didn't activate AutoLab, so you can't submit yet. AutoLab will still give you a 500 error if you go there. So I'll upload the roster at least before the homework's due. But let's talk about the first homework. It is on the course website. Click homework 1, and it's going to take you to the doc explaining all of the requirements for this homework. So I want to go through them quickly. The course is structured around the homeworks. So for homework 1, we have 3 weeks where I'm going to show you everything that you need to do to be able to complete this homework assignment. So you won't know how to do most of this yet, obviously, because we haven't covered any material. But we will get through all that in the next 3 weeks. So I won't go too long on each requirement specifics, but I do want to give you an overview of what you're going to be doing for this homework assignment. So the first thing, we will be using Docker for all homework assignment submissions. The Docker lectures won't come for next week, I think. It will be the Docker lectures. Docker is a way to be able to run your app on effectively any machine. At least that's the goal. So when you run your machine on you run your code on your laptop, and then you submit it to AutoLab, when the TAs grade that code, they're going to be able to run exactly the same way because they're going to run Docker, which is effectively a startup script. It's going to create a completed container, which is like a lightweight VM, and then run your startup script, install anything that it needs to install, and set up everything that you tell it to set up for your app. So it's really an incredible technology that's taken over all of software engineering in a pretty phenomenal way. This idea of containerization, and mostly Docker is the technology that's used for that. So most apps that we use, that we enjoy, they're deployed using Docker because it really streamlines that. You don't have the issue of, well, it worked on my laptop or it worked in my development environment, but when I pushed to production, nothing worked. Docker's goal is to solve that. This really helps in this course since you can use whatever language you want. We don't have to worry about how to run your app. We're just going to run Docker. And no matter what language you have, we don't even have to really care. As long as it runs and it works, we're going to use Docker to run it. So that is a requirement for all of the objectives of this homework. But I don't recommend starting with Docker, of course, or else that would have been the first lecture. We would have been talking about Docker today if I wanted you to do that first. Get something else working on your app without Docker, and then try to add the Docker layer onto it. It's just so, and the reason for that is so you have something to test. Testing Docker without having an app to test, it's very difficult. If you have something to test, your Docker is set up. That's more recommended. And then specifics on how we're going to run Docker. We're going to run very specific commands. So you can run those same commands on your laptop and make sure that it's going to work the same way the TAs are going to use it. All right, and then your first objective, what else but hello world? Right, most of this is setting up your TCP socket server to be able to listen to connections and then respond to those requests over those connections. So the first one is just the standard hello world. Somebody's going to make an HTTP request for the path /hello. If that doesn't make sense, don't worry, we got several lectures on it. And respond with just the text, hello world. So this, and at this point, that will effectively be a web server serving a website. It's not a very interesting website, but it will be a website. It doesn't even use HTML, but it is technically a website. So at that point, you'll have your first website up and running built on a TCP socket. So let's add some more features to that. We're going to add a second path /hi that's going to redirect to /hello. So this is a path where this is common in industry where a company is going to reorganize their paths for their web app. And the old paths, they want them to redirect to the new paths. They don't want everybody's bookmarks to be invalid. So they're just going to have the old one redirect to the new one. So we're going to simulate that by adding a second path hi, which is going to map to redirect to hello. And also adding a 404 page. If anything is requested that isn't specified in this doc, send them a 404. Just send them some plain text message that says content not found, just something to notify the user that what they're looking for isn't there. In each of these, all the objectives are going to have testing procedures. I mentioned this Monday, but it's worth repeating. These testing procedures are the same testing procedures that I give the TAs. I don't give them like a separate set of instructions on how to grade. This is how they're grading. If they go through this testing procedure and everything works, you're going to get full credit. So you can go through that same exact testing procedure when you're done with the assignment. I would recommend downloading your, submit it to AutoLab, downloading your zip in a fresh directory that you haven't been working in, and go through the testing procedures and make sure it works, because that's exactly what the TAs are going to do. If that works for you, there's no reason for it not to work for the TAs, and you'll get full credit on that. So I don't want to hold nothing back. You and the TAs have the same information of how everything's going to be graded. And I try to be as specific as possible with these testing procedures. Like there's quite a few steps. Like this start with, oops, I shouldn't say objective 1. I'll leave it like that. But that means follow the Docker procedure to run Docker, and then follow the rest of the testing procedure. Next, we're actually going to host some more standard web content, HTML, CSS, JavaScript. We're going to host these files, and you're free to write your own, but if you don't want to mess with front end, it's not a front end course. I gave you a sample site. It's not a very interesting site, but admittedly, but it's just something so we have something to serve with our server. So serve these at least 3 different files to be able to effectively have a web server that's serving a web page. Next, serve a text file that contains UTF-8 encoded characters. It's very important to support UTF-8 these days. Pretty much everything does, and we're not going to be an exception. We're going to serve UTF-8, and we're going to serve it properly. There are some caveats to serving UTF-8 that we don't have to face when we're serving ASCII-only text, and we're going to talk about those, and you're going to handle that in Objective 4. And finally, hosting an image, which admittedly, it's actually easier than hosting, serving the other files, but it's a different procedure, so it's a different objective. Host an image, we're going to have this adorable little kitten on there, and there's a flamingo on the page here. When you do Objective 3, the flamingo is not going to load until you complete Objective 5. And that's the homework. Submit all of your code as a zip file to AutoLab. Again, I haven't uploaded the rosters yet to AutoLab. I created the course, but I didn't upload the roster. There's nothing there anyway, and once I do have something there, it's literally just, here's where you submit homework 1, and then you can click there to upload your zip file. So you're not missing anything by not having access to AutoLab yet, but I'll get the roster. I don't like doing the rosters too early because the roster changes during add drop period. So after add drop, I'll do the final upload. I might not even upload the roster before then. Then I only have to do it once. But if somebody pushes me and you're getting anxious, you want to submit, somebody's done early and they want to submit, I'll get that roster uploaded. Grading. Grading is a non-linear scale in this class. So I want to talk about this. For each objective is weighted equally. So we have 5 objectives. Each are 20% of your homework assignment. Each of those you're going to get a 0 to 3 grade. A 3 means you did it, the TA followed the testing procedure, everything worked, you're awesome. You got full credit. A 2 means they went through the testing procedure and it worked, but there's something off. You did technically get it right, like you might be able to argue that you got it right, but there are some issues with it. Something just wasn't completely correct. There's some part of the lecture content that you were supposed to implement that you didn't quite implement in the right way. Maybe have a slightly incorrect MIME type. Well, I can't get into specifics because we haven't talked about anything yet. But something's a little bit off. 1 means you're just wrong. You attempted the question, importantly. You made an attempt to complete the objective, but it's just flat out wrong. So anything where the testing procedures did not go well. So anything that doesn't qualify you for a 2, it's going to be a 1. And then you only get a 0 if you didn't try at all. If you didn't even attempt that objective, and for those determinations, like if the TA goes through the testing procedure, nothing works at all, then they're going to crack open your code and see if there's some evidence that you gave it an effort, gave some effort to complete that objective. if they find anything, if they find a good amount of effort there, it's going to be a 1. If they don't find anything, you literally just gave up. That's the only way you're going to get a 0. You just didn't try, or goodness, don't do this, please, but just didn't submit the entire assignment and got 0s on all of the objectives. Please, please don't do that. But that's the only way to get a 0. And then the grading is nonlinear. As long as you get a 1, you get a 60 on that objective. This is my way of saying, my goodness, I don't care if you're completely lost in this class, but you gotta try. You gotta try. If you try, I'll reward you. You'll get those 1s as long as you have something there. Give us some reason to give you a 1. I'll give you a 60 in this class if you get straight 1s across the board. Which I changed the scaling. Let me double check just before I say something. Yeah, 60 is passing. I think it was a 70, and I changed it to a 60 this semester. So even if you attempt every single assignment, and you get, and likewise on your project with your team project, if you attempt everything, I'm going to get you passing this class. You don't have a great grade, but you'll pass this class. In being elective, I don't want to be too strict. Like in 116, for example, I have to be more strict because you need that content to move on with your education. This is an elective. I can do things a little differently. I don't have to have that strict of a grading where I need you to know all of the content in this course. Like, at least show me that you're trying. I assume you're here because you're interested in web applications and building web applications. So, enjoy the content. At least try everything. You'll at least pass the class. And of course, if you want a good grade, really study the material and do well in the course. Then you can start getting those 3s and getting your A. But it's pretty hard to fail this class unless you don't try, which I find is true with all classes, at least the ones I teach. The only students who ever fail my classes are the ones who give up on me. So just don't give up on me. I'll at least pass you. And that's all I got. All right, any questions on this? Oh, and a reminder, I do have Discord open, the lecture channel. I'm looking at it right here. So if anybody wants to ask questions on there as well. But any questions? Yep.
There's no like 2.5?
No, I push my TAs. So the question is, there's no 2.5, right? I push my TAs to put you in one of these 4 categories. If they have a borderline call, to be honest, I tell them to just, if it's a 2.5, just give you the 3. But
so like you get 14 out of, for this one, 14 out of 15 for the whole part. If you got like 1, 2. Is that how it works?
Kinda. So the question is, if it's a 14 out of 15 of the whole homework, I know last semester I've seen students always want to add the points up, but you can have different, like maybe 14 is a bad example, but there's no like total score for the assignment because, so the max will be 15, like a 12, not all 12s are created equally. For example, like if you have 4 3s and a 0, that 12 is very different than 3, I have to think, 3 2s and 2 3s. Those 2 12s are very, very different. So there's really no total on the homework assignment. I know that's how you like thinking about them, and that's fine. But yeah, there's no like 14 on the entire assignment, but there would be, if you had 4 3s, which are hundreds, and then 1, I mean, the math is going to kind of work out that way, isn't it? No, it isn't. And then 1 2. That's going to average to, I didn't expect to do all this math this morning. It'll average to some number. 86, I want to say. 96. And that'll be your overall score for the assignment. So your 14 out of 15 is not 14 divided by 15. That's not your overall score, just because it's a nonlinear scale. All right, any other questions on this? And this will be the grading for all of the homework assignments. I'm going to follow this. The TAs are going to follow this. And there's going to be 5 objectives on all of the assignments. All right. Let's get to some content. All right, I got to remember how to do in-person lectures again. I'm going to try to teach from the podium, but I have to use the page up, page down buttons. for now. I haven't figured out a better reason, so I gotta stay close to this keyboard. I'm sure that'll be fine though. Oh, one more quick announcement before we get into content. We do have it set up where my TA Mike, who's amazing, is uploading the videos to YouTube. So the first lecture, Monday's lecture, is on YouTube. So if you don't want to go to UB Learns, there will obviously be a little bit of delay because he's downloading the Panopto video, doing a little editing, and then uploading to YouTube. But if you want to wait for those YouTube videos, you can watch them on YouTube if you don't want to go to UB Learns. If you want to watch the lectures as soon as they're uploaded to UB Learns, of course, you can go there and go to Panopto and laugh at the horrible auto captioning. It's so bad. All right, so let's talk about what the internet is. Today's lecture is going to be a bit of background of what we're going to do. The content gets a little technical, but I'll keep it at a higher level. I won't get down into the dirty details because you won't have to code anything that's covered in this lecture. This is more of drawing the map and figuring out where this course lives inside of the world of the internet. So specifically, we'll talk about networks and TCP/IP. So let's start with networks. So here's a network. Oh my, just getting used to this again. This is the first time I've done slides in person since COVID. I'm like, how do I see what I'm presenting? I guess I look at this one. I forget how I do this. So I've tried to look at this, but I'll be staring at that thing. That's not what I did. I would stare at this, right? Or just memorize my slides. So, so the internet is a network of networks. You might have heard that before. And I want to expand on that and show what that means. The internet is a network of networks. And some of this content, if you had 199 with me, some of these slides even are duplicated. This is like 3 lectures of 199 all crammed into one, though. I go really fast with this stuff, faster than 199 at least. So at the lowest level, we have our local area network, which is what we're familiar with. This is what we see in our homes. We have a router connected to a modem that's connecting to the next network, and that router, and this is where we usually have Wi-Fi. That's what we're going to connect our devices to. And I can finally do this again, but I don't see any up here, I guess. No, those are not. I miss being able to point to the wireless access points, but I don't even see one in this room. And it's disappointing. Anyway, probably out in the hallway, there's a wireless access point. That's what we're connected to connect to UB's network. And this week, it's been not great. It took a while for my laptop to connect to it. Question on Discord, when is homework 1 due? It's on the course schedule. I don't remember off the top of my head, but I think it's like the second week of, maybe the first or second week of the homework 2 content. But it is on the course schedule. So this is what we're used to. We're used to seeing this kind of hardware around. And this is the only place in the internet, maybe that's a little too strong of a statement, but for most use cases, this is the only place in the internet where we're going to see a wireless technology. Once we go a step up in these following steps, these are all going to be wired. Once you hit that wireless access point, there's a physical cable connecting that to the rest of the network and the rest of the wireless access points. And then the Wi-Fi is only from that wall over to our laptops, to our phones. Well, phones, unless we're connected to mobile data, then it's a whole different technology. We'll connect the wireless to the tower, and then the tower is hardwired into the internet. But once we go up another level to the ISPs, we have physical cables, and these ISPs are connecting networks, connecting our LANs at a city or a regional level. And we can see these wires. You look up at the telephone poles. Those are power, obviously, telephone, but also our ISPs, our internet connections, are physical cables that literally just go up into these poles or underground and plug our houses into them, and then we're connected to the network. Same idea as our local area network, assuming for your Ethernet connected devices anyway, where you literally plug your device into the router. We're doing the same thing here. We're plugging our router into the modem in the wall, and then we have cables that are connecting us to other houses at a city or regional level. Tell this thing to not fall asleep. One step up from that, Oh my goodness. If you accidentally click end, you go to your last slide. After that is the tier 1 networks. These are the networks, these are the companies, the organizations that the ISPs pay for internet. So the ISP, they're not the internet themselves. They pay the tier 1 networks to be able to get internet access. And if anything, if I could point to anything and say that is the internet, I would point to the tier 1 networks as a whole. This group of networks is what we consider the backbone of the internet. These networks are connecting networks at like a national, at a continental, and even a global scale. That's the level of the tier 1 networks. And these networks, they often / always have peering agreements with each other, so they can use each other's networks free of charge. So all of the tier 1 networks, I shouldn't say all, but the tier 1 networks get together and they say, you can use my network if I can use your network. And they do this all free of charge. So they can all use each other's networks with the idea of, well, they're going to use my network and I'm going to use theirs. If we charge each other, everything's just going to be a wash anyway, because we both have tons of data demands. So let's just say we can use each other's networks and call it a day. Instead of metering everything and going through all that, they have these peering agreements. So since having access to one tier 1 gives you access to all tier 1s, that really is like the internet. That's the backbone of the internet right there. I hear some of these companies, you might have heard of some of these, some of them you might not have, but these are the companies, at least in the United States, that really are that internet, are that backbone of the internet. But there's one problem with these maps. Oops, I'm not talking about that yet. So the ISPs are paying the tier 1s for internet access, and the tier 1s have peering agreements with each other to be able to use each other's networks. So that implies that we have these massive networks, these very huge networks of wires, of cables scattered throughout cities and regions and states and countries and continents. At some point, those networks have to plug into each other. And that happens at places called internet exchanges, like this one at 60 Hudson. I think it's not the whole building, but I think the 6th floor, I want to say, is the entirety of that floor is the internet exchange, and then like the floor, it's really cool, I should have had exacts, but I think like the floor above or below it is just filled with diesel fuel and generators as a backup in case the power grid gets knocked out, which caused some controversy, having such a huge amount of fuel sitting there, turned some eyes, yeah. It alerted some people. But nevertheless, it is there, and this is what the inside of an internet exchange looks like. As you can imagine, it's just a ton of friggin' cables going all over the place with routers and everything needed to direct traffic through the internet. So, oh, damn it. That was the buildup I was trying to do. Anyway, so there's a problem with the pictures that I showed you on the previous slide. They're all just the United States. But as we know, we can connect around the world. We can connect to other continents, and we can connect across oceans. And that happens literally by taking giant cables, plugging one of them on one end of the ocean and one of them on one end at the other end of the ocean, and plugging continents into each other, which always amazes me that with all the technology and all the advancement that we have these days, the best solution we have to cross continents is just getting a big old cable and plugging in continents to each other. That's still the technology we're using. There is the technology available to use satellites, but the ping is just too slow. If Elon Musk gets, I forgot what it's called now, Starlink. If Elon Musk gets Starlink, that once that gets up and running, that might be able to replace these cables. Those are lower orbit satellites than the ones that have been used for the internet, which should have lower latency. So we'll see how that goes. I'm hopeful. That would be awesome, just having global internet access like that. For now, it's literal cables. Any newer cables are fiber, just plugging in fiber cables and plugging these connects in. The internet is a very physical thing. We like to think of it as this, the cloud and this magic Wi-Fi technology, but Wi-Fi is literally going from here to somewhere out in the hallway where I don't know where it is. But from there, And then if I'm connecting to someone in Beijing, it's literal cables from that box out in the hallway all the way to China. You can follow a literal physical cable. And then the last like 20 feet or whatever of the Wi-Fi of the person I'm connecting with, that's going to be over the air. Everything else is actual physical cables. The internet's a very, very physical thing. Yeah. What happens when a fish gets hungry? That's happened. Yeah, those cables have been severed before, especially the early ones, the first ones. So they found ways to reinforce them and make these things frickin' durable. I had in 199 when I cover this content a lot slower. I have a video where a shark actually walks up to one, bites it, and goes, "Oh crap!" It probably cracks a tooth or something. And goes, "Oh, I'm not messing with that." And swims away. So they're big, and they have huge boats that'll have these massive spools of this cable. They'll unwind it, and I don't know. It's again, I had pictures I do in 199, but expensive, yes, like billions. It's
split it up because like the internet exchange is a bunch of Ethernet cables, but I assume there's not like 1 million Ethernet cables inside of this.
There's not 1 million, but there's a lot of fiber in those cables. They have a lot of bandwidth, as you can imagine. They have to have a lot of bandwidth. Yes.
Where do VPNs come from? Like connecting to the network?
Where do what come into play?
What do VPNs do?
VPNs?
Yeah, VPNs.
They don't encrypt. What they'll do is, so a VPN is a server that'll sit, like say you have a VPN here because that's the one I can reach in Australia. Say you have a VPN here you want to connect to and you want to pretend you're in Australia. What you'll do is send your request, whatever web request you want. Say you want to access Netflix and you want to watch some Australian TV, Australian shows or something. What you'll do is send that request, hey, I want to watch this show. Send that to your VPN, and your VPN sends the request to the server, Netflix server in Australia. And then to Netflix, it looks like it's coming from this VPN. They'll send the response to that VPN, and the VPN sends the response back to you. So they're acting as like a middleman for all of your communication, and proxy is probably a better term for that. They're acting like a proxy. You work through them to communicate. The VPN itself, I might have misspoke a little bit there. The VPN itself doesn't have anything to do with encryption, but most VPN services will encrypt all your traffic. But that's true with anything on the internet these days. Because, try to go to a website using HTTP. It's really hard to do these days. Everything's using HTTPS, which means it's encrypted. So pretty much everything's encrypted by default. But VPNs, the services are going to make sure everything's encrypted. But a VPN, that technology itself doesn't have to be encrypted. You could send that message to the VPN unencrypted. Any VPN worth their salt, any company doing that is going to encrypt. Oh yeah, I definitely violated AI. I stole Nicholas's dark theme from 116 to 312 and 442. So a lot of those cables are paid for and supported by the tier 1 networks, but even some private companies, VPN, no, tier 1s are private companies, but some service providers, content providers, also have their own cables. Google specifically, Facebook has some. I wouldn't be surprised if Amazon has some as well. The major players in tech are saying, you know what, it's expensive to pay these tier 1s because they have a lot of bandwidth that they have to cover. So they'll build out their own networks. Google has a pretty massive network built out, including some of their own, the green lines here, some of their own oceanic cables that they've laid just so they can serve their content faster. And then those cables, of course, only carry Google content. That's why when you load up YouTube, you pull up YouTube, your stuff's going to load like crazy. Unless there's some other issue like UB's Wi-Fi, that YouTube video, that's going to load quick. Because Google spent billions of dollars building out their network, so they don't have to rely on the tier 1s. If the tier 1's having a bad day and the servers or the routers are bogged down, you're still getting Google content. But if you go to another video service, another site, you might not get that speed. Also, like Twitch can do what they do because they're Amazon. They're owned by Amazon. They got Amazon's network and all of their power behind them. Yeah. Mm-hmm. Yes and no, kind of. But the second half of the lecture, which I got to check my timing, we'll talk about that a bit. So the routers are you're gonna send your information to that access point, and then the routers are gonna decide how to route your packet through the internet to make sure it gets to the right server. And this is, you hear Google Fiber trying to go into cities and act like an ISP. That's Google saying, hey, we got all these cables laid. Why don't we just start acting like an ISP? They're basically their own tier one, their own private tier one right now. They're like, we could go into some cities and start being our own ISP too and control the whole frickin' everything of the internet. And I have no other comments on it. But they're looking at, some Google executive looked at this map and said, yeah, why don't we just be also an ISP? So those cables are going to connect us to data centers and server farms like this one. This one is actually pretty close to here. You could get there in like 15 minutes. This is Yahoo's data center in Lockport. And these are things like server farms like this are all over the planet. Any of the big tech players have tons of these. Google, of course, has them all over the place. Netflix has these all over the place. Amazon, of course, Microsoft. And these are just filled, these buildings are filled with computers, filled with servers to be able to host the apps that we need. So you think of a service like my mind keeps going to YouTube today, but so you think of a service like YouTube and think of the bandwidth required for that. Think of the processing power required for that. For how many of us use a service like that? If they have millions of concurrent users, what it takes to serve all of that content. Think of just like downloading or uploading one movie from your own laptop, and then multiply that by millions. And what that takes this kind of processing power, multiple of these spread across the globe to serve a huge site. I mean, think of Yahoo, which is this one. Yahoo has multiple data centers like this, and they ain't exactly as popular as they used to be. They're not like a huge site. They still need data centers like this to be able to run the apps that they run for their user base. Inside of one of those things, you just got racks and racks and racks of servers. If you've never seen one of these before, this is just a machine. It's got the same type of hardware, slightly different as you have in your laptops and your desktops, but they're designed, they're shaped to fit in server racks. That's what we call a physical server. It's the same kind of technology. It's got a CPU, it's got RAM, it's got hard drive, but they're made to slide in these so we can have racks and racks and racks of them. The hardware is a little bit different. They have different types of processors like Intel Xeons that are designed to run 24/7. These things never shut down. You put them in there, and they just run, ideally forever, until they break, then you replace them. So racks and racks of those, and then multiple buildings of those, and then multiple data centers. That's the kind of computing power these companies need to run the apps that we enjoy. All right, so everything's plugged in. We have these cables running all over, plugging our wireless access points and our routers from our networks into our ISPs, into our tier ones, and then into potentially other ISPs or directly into data centers. The tier ones, I'd say most of them are just plugging directly into data centers. Like UB has a tier one connection. We don't mess around with ISPs. We're not, UB doesn't call up FiOS and order internet. We're plugged in directly to a tier one. I mean, it's bad because of thousands, tens of thousands of people all using the same Wi-Fi. The air can't handle that. The air is the limiting capacity, the limiting factor. Later in the semester, that always calms down, but week one is always bad because everybody's here, everybody's using the internet. Everybody's using the Wi-Fi. So what do we do with these cables? The answer is protocols. We'll talk about a lot of protocols in this class. The first two, Internet Protocol and TCP. Internet Protocol is going to determine how we communicate. So when we plug in to the Internet, we don't want to, if we send a message over the Internet, we don't want that just blasting over every single wire and sending that to every machine on the network. Instead, we're going to send it to a specific device, which we specify through its IP address, its Internet Protocol address, which is where that machine lives on the Internet. So all of our devices connected to the Internet right now have IP addresses, and then that IP address is where your device is on the Internet. And that's how we get the information to where we want it to go and not where we don't want it to go. When information is transferred using the Internet Protocol, which literally is the protocol of the Internet, everything that's transferred over the Internet uses the Internet Protocol. Your data is sent in a packet or a datagram. I usually use the term packet. And these packets are pretty small. They're on the order of kilobytes. And this is the only way you can transfer information over the Internet, is sending a packet of data. And the Internet uses something called packet switching, which I wanted to talk about, but I don't think, I do want to get through my slides. So we're going to send an order of kilobytes amount of data over the Internet, and that's the only thing we can do over the Internet. This packet is going to have some information. Most importantly, the destination IP address. Where is this thing going? Which you can think of as a mailing address, a physical mailing address. That's how your information is going to get routed through the Internet and make it to that destination machine. IP addresses look like this. IPv4 addresses look like this, where it's going to be 4 numbers ranging from 0 to 255, which honestly we do just because it's more human readable. To the machines, this is just a 32-bit integer. So we have a 32-bit int that's going to determine where this packet's going. And we use prefixes. I can't point to that. I have to point to this. We have prefixes. Like, for example, one of Google's prefixes is 172.217, meaning anything that starts with 172.217 is going to one of Google's servers. And the routers of the Internet know what to do with that. Without reading the entire address, they're just going to read the prefix and say, oh, this is Google's. I'm going to send this to Google. And once it gets to Google's network, Google's going to decide what to do with it after that, what specific machine to send that to. But the routers outside of Google's network don't care. They just need to get it to Google. Big problem with this. We do some math and see that we have 4.3 billion IP addresses, which is a lot, but not really. That's not even one for every human on Earth. That's not a lot. So we had this big problem where we're running out of IP addresses because enough people were using the Internet. 4.3 billion probably sounded like a lot to the original inventors of the Internet when there were like 3 people using this technology. But, I mean, for it to blow up like this, 4.3 billion, not enough. So some years back, quite a while ago by now, we needed a solution, and that solution is IPv6, which uses 128 bits, which gives us this many possible addresses, which I think that should be enough. I run the risk of being as naive as the people who propose IPv4, but with that big of a number, I think we're good. I think we'll be okay. Yeah.
So in the server farms, do all those computers have the same address, or do they each have
It depends how it's set up. Depends on the data center, but I would guess that they'd have one address, and then they'd have internal routing to figure out what machine to give it to. They'll each have a separate address on their LAN, but to the outside world, I would guess that it would be just one or a handful of addresses. So I'd say we have enough. This is a big transition. All the routers of the Internet had to be updated to support both IPv4 and IPv6. We still use IPv4. You still see those addresses all the time. But once we run out of IPv4, we use IPv6. So for example, UB has a certain number of IPv4 addresses. And once we exceed that number, UB is going to start giving you IPv6 addresses. So you can check your IP that you have that UB gave you when you connected to the Wi-Fi. And sometimes it's IPv4, sometimes it's IPv6. but we don't have enough IPv4 for everybody, 30,000 people who want to connect to the internet simultaneously. But we have a solution. You can access websites, like the IP address is the only way to access a server or another machine on the internet. So you can go to those machines directly through their IP, but as humans, we don't really like that. So we have another layer on top of this called DNS, Domain Name Service, where you can buy a domain name and link that domain name to your IP address. So we type google.com. That google.com gets sent to a DNS server. The DNS server says, here's your IP address for Google. And then your browser makes a request to this IP address. But you can't make a request to a DNS domain name. That domain name just goes to the DNS, gives you the IP, then you make the request to the IP. And most of this is invisible to us. We just type google.com, and we get a request to that IP address, or one of Google's other IP addresses. They got a lot of them that all go to their website. They have a lot of web addresses. Some sites do block this. The second one, I made this slide a while ago, so I don't even remember what that site was, but I found a site that doesn't allow direct IP access, which is something that something we can do. I don't know why exactly sites do that, but it is something that some sites do. So the Internet Protocol itself is going to specify the structure of a packet in the Internet, which is going to look like this. Every packet that goes over the Internet, at least over IPv4, this is an IPv4 packet header, is going to look like this. So over those wires and over that fiber, we can only send two different things, a 1 or a 0. There's light or there's no light. There's voltage or there's no voltage, high voltage or low voltage. We can only send two things. Everything in the world of computer science, in the internet, in our machines, everything is 1s and 0s. That's it. That's all we have to work with. As we go through the semester, it's going to be very apparent to us. It's all we can send over the internet are 1s and 0s. But we can communicate an extreme wealth of information over the internet. And how we do that is through protocols and encodings. Today we're talking about protocols. The IPv4 protocol says when you get a packet, it's just going to be 1s and 0s. But this is how we're going to assign meaning to those 1s and 0s. So when you get an IPv4 packet, when a router gets an IPv4 packet, it knows the first 4 bits of information are going to encode the IP version of this packet. So it knows whether it's v4 or v6. It's going to know that by reading the first 4 bits of information. If it's an IPv4, it knows the next 4 bits are going to be the IHL, then the type of service, then the total length. And it's going to read this many bits. There's always going to be this many bits for the header information. It's going to read all this information and know that it's in this order. So when you're sending a packet over the internet, if you put the destination address right here, that the routers of the internet are going to know to look there, exactly there, in this sequence of 1s and 0s for the destination address. The router can read that, figure out where this thing's going, and then route it to the appropriate next router. We also have total length, is a very important piece of information. After this header is going to be the content of the packet. The Internet Protocol does not care about the content of a packet. All it cares about is routing it to its destination. So you have the content of the packet after this. And the total length is going to tell the router how many bytes of information to read after this header. It's just going to read that many bytes. Then it knows it hit the end of that packet, can send that packet off where it's going, and then the next bit of information is going to be the next packet that it needs to route. And this is how protocols work. This is the magic of computers, really, is to peel that back. And by the way, a lot of this course is just destroying magic. There's no magic of the internet. It's a lot of protocols. It's just agreeing which bits mean what. And that's a lot of how the internet works. Demystifying magic is what we do here. So sorry if you want to live in that world where the internet is this magical cloud that's about to get shattered every day in this class. And then once a router reads that, it's going to read the destination address, look up in what's called a routing table, and figure out what is the next hop for that packet. It's going to decide where that packet's, not where it's going to go, not its final destination or anything, just the next router that handles that. So there'll be this routing table which says for some range of IP addresses, maybe any IP address with a prefix of 150 or so, that's going to go to this router. If it has a prefix of this, it's going to go to this router. If it's this exact IP address, it's going to go to that router. It's going to look that up in its routing table, send that packet off to the next router in that path, then completely forget about it and move on to the next packet in its queue, and then route that next packet. That's all a router does. And there's a big problem with this, is that it just sends that packet off to the next router and then forgets about it. So what happens if that packet never makes it to the next router? What if there's a severed cable? What if there's a solar flare that flips a bit, disrupts the whole thing? What if there's a power outage? There's any number of things that can cause what's called a dropped packet. Any number of reasons that packet might not make it to its destination. So, and the routers are designed strictly for speed. They're not designed for reliability. The internet itself is an unreliable network. When we send something using the internet protocol, there's no guarantee that it's going to make it to its destination. The routers are just going to send it to the next hop, and then for any number of reasons, it might not make it to where it's going. So we're responsible for making sure information is communicated reliably over the internet. And by we, I mean developers, software developers. This is the world of software. At this point, our applications have to care, which I don't talk about the network stack much in this course, but at the application layer of the network stack, we have to care about, that's not true, oops, that's why I don't talk about it, because I already misspoke. but the next layer of the protocol, not the internet itself, has to care about making sure that we communicate reliably. For that, we use TCP. In this course, we use TCP for all of our internet communication. TCP is going to establish a connection between a client and a server, and then communicate information over that connection instead of just sending individual packets of information. So to establish this connection, TCP is going to do what's called a three-way handshake, where the client, which is going to be like our browser, is going to send to the server, which is going to be whatever website we're trying to connect to, the server for that website. We're going to send them a sync packet, which is nothing magical, it's just a random number. It's going to send a random number to the server. The server is going to respond with that random number plus 1, some real tough math, and also another different random number. The client's going to do the same thing, take that sync, take that random number, send it back with that plus 1. And at that point, we have established a TCP connection. Now, this might seem silly, just random numbers and then adding 1 to them. What's the big deal here? The important part of this is that we know that the client and server are speaking the same protocol, able to interpret each other's messages, able to decode a message, extract a number, convert it to an integer, perform a mathematical operation, re-encode it, and then send it back. And then the client's able to read that encoded message. So a lot has to go on to be able to just add 1 to a number and send it back. And that gives us verification that there is a machine on the other side that also speaks TCP. And that's a good thing. We can establish a connection and start speaking TCP because we got through this three-way handshake, so we both know that each other speaks TCP. We're not just sending packets into nothing, into the abyss. We have an established connection. Once we have a connection, we can start communicating. And for this, a lot of the messages that we send over the internet, a lot of the information we want to send, isn't going to fit in a packet that's a few kilobytes. Most of the time, we're going to have to break that message up into multiple packets and send them all to their destination. So TCP is going to add this idea of sequence numbers, where we have all the packets that constitute your message, whatever you're sending, break them into packets with sequence numbers, and then send them off to their destination. Now, on the other end, if there's a dropped packet in there, you can be like, hey, I need you to resend packet 15 to me because I didn't get that one, but I got the rest. And once all that, the resends happen, and you get all of your information, then you can reassemble it, reassemble all the payloads of all the packets, and now you have this large message that was sent as individual packets over an unreliable network. So what TCP does, it gives us reliability. And it also adds the idea of port numbers. And your TCP port number, along with your IP address, that's where we start getting TCP IP. This is how we communicate reliably over the internet, is using TCP and IP. Commonly just said as TCP IP. In your code, so everything today, you're not going to have to handle. You can pull in libraries to do that. Where you start your development for your homework assignments is with a TCP socket server that handles the three-way handshake and handles sequence numbers. It's going to handle all that stuff for you. It's going to break information into packets, speak internet protocol. All that stuff's going to happen for you. We're going to assume that all that works, and you're going to pull in a library that starts with a TCP connection already established, so you can reliably communicate over the internet. And then we're going to speak HTTP after that and build a whole bunch of stuff. If you're interested in more TCP IP, Modern Networking Concepts has you covered. But that's where our TCP IP and networking stops for this course. And we'll pick up with HTTP on Friday. And I'll see you then.